All right, let's get started. So for the next couple of lectures, we'll spend some time to talk about deep learning because some of the students don't have any background in deep learning. So we'll spend a couple of lectures, kind of like a crash course about deep learning. Okay, so I'm sure you guys have heard all these buzzwords, right? Artificial intelligence, machine learning, and in particular, deep learning, right? So, deep learning is essentially used pretty much everywhere, right? Speech processing, image processing, natural language processing, right? You've heard deep learning is kind of taken over the traditional machine learning and make significant improvement in terms of performance. So in general, artificial intelligence can have a very broad scope, right? Basically, it means it's have like the human intelligence, right? So you got a program that can sense, reason, act, and adapt. So to achieve artificial intelligence, right? So machine learning is very important, right? Because we want to using machine learning to develop the algorithm. The performance can improve as they learn from more and more data, right? Learn from the experience, learn from the data. So it's a smaller scope, within artificial intelligence. And deep learning is a subset of machine learning, right? Because machine learning, we have this classical machine learning, mostly statistical machine learning approaches. So deep learning is a subset of machine learning, right? Specifically using neural networks to learn the representation or learn useful features from the data. So these are kind of like how these different concepts, right, plays out. And so you may be wondering, right? So why deep learning, right? Why do we have to use deep learning, right? What happened, before the deep learning was born, right? So let's using image processing or computer vision as an example, right? Before the deep learning, we do have a lot of classic machine learning algorithm that is able to do all kinds of vision tasks like image classification, object detection, segmentation, tracking, etc. So the general pipeline the first step is you need to build a feature extractor, right? Trying to extract some of the meaningful features from the image or data, right? Because machines view these images as these giant matrix, right? We need to extract some useful information that is maybe discriminative enough for the later classifier to distinguish different objects, different classes, right? So for the before deep learning, we have a lot of efforts have been devoted to how can we come up a very effective feature so that later you can use that to do a very good job on classification, recognition, or detection. Right, so these are called hand-engineered feature, right? Because we using some of the knowledge, maybe physics inspired or maybe other, signal processing based, feature extractor, right? So people using edge detection, right? Detect those edges and use that as a maybe more effective feature than the raw pixel values. And people can using, signal processing technique like Fourier transform, DCT transform, or wavelet transform, right, in the frequency domain and extract those frequency components, coefficients as features to do the later processing. So these are hand engineering feature, right? We need expert knowledge, right, to understand what might be the important information we want to extract from the image. So once we have these features, then what we do is we try to build a classifier, right? So we have a classification module after the feature extraction. So this can be some of the classic classification method like linear regression, logistic regression, decision trees like random forest, and support vector machine, right? So before the deep learning, support vector machine was very popular and also performed very well in terms of a classification task, right? Then we can generate output, right? For classification, we can generate the class label for this particular input data. So we kind of have like this kind of cascaded stages, right? Feature extraction, classification. These are the two main components. There may be some other components like data pre-processing, right? So you want to do some data cleaning or some pre-processing to make it easier, or data normalization, right? To make it easier to fit the later classification task. But feature extraction and classification are the two very important component in this classic or conventional machine learning paradigm. So for the deep learning, the one main difference is that we no longer separate these two processes as feature extraction and train the classifier. So pretty much we learn everything in the single unified framework, right? So we have this neural network, and we trying to learn what kind of features we want to extract from the data and how we can use that to do the classification. So basically the feature extraction and the classification are unified in the single framework. So you basically just learn this mapping function, right? You have the data, I want to using this mapping function to the class probability, right? What's the probability of this image belong to a cat or no cat, right? So this is the one fundamental difference as compared to this conventional machine learning and deep learning. So here, just some of the examples, right? What this deep learning is able to learn from these raw data, right? This is the data-driven approach. We learn these kind of features from the data. So these are some of the examples, right? What the deep learning, the deep neural network can learn from the data, right? Low-level features, middle-level features, and high-level features. We'll talk more on this in the later slides. Okay. And also, there's a couple of reasons, right, why deep learning take off, right, after this 2012 ImageNet. Actually, some of the techniques exist a long time ago, right? For example, the well-known stochastic gradient descent, right, for optimization is actually built in 1952, right? So, and the perceptron is the early idea of this kind of neural network is invented in 1958. But at that time, doesn't really see much of the success of the neural networks. But now there's a couple of reasons, right, for the neural network come back and really take off and triumph every field, right? Image classification, speech, natural language processing, and multimodality understanding. So there's here a list couple of main reasons. One is the big data, right? So we are living in this kind of big data era, right? So we have all these IoT devices, cell phones, other type of cameras. We can basically constantly record or collect data 24/7, and we also have those social media platform like Facebook, Instagram, YouTube, right? Users upload data to these platforms. So essentially, we have a huge amount of data, right? And before, we don't have these kind of luxury, have a lot of data to build a very large data set to train the deep learning network. So for 2012, right? So this ImageNet is released. They have a challenge, and this is a million scale data set, has a lot of data, 1,000 classes, and this is like the largest data set for image classification at that time. And they were able to using this kind of big data set to train the deep learning model so that the model can learn very well from this huge amount of data. The second reason is the hardware, right? So before, we don't even have GPUs, right? The GPU is graphics processing unit, right? Has massive parallelization, so you can do matrix operations very easily on these highly parallel computing hardware like GPUs. So before we don't have GPUs, right? We only have those CPUs. So there's a limited computing power, right? So at that time, you cannot process a lot of data. You cannot build large networks, right? So the neural network has a limited capacity to learn meaningful information from the data. And we also have, a lot of software, right? So you don't have to, code everything from scratch, right? You implement a stochastic gradient descent or, batch normalization, those things from scratch. So all these, there's mature software like the TensorFlow, PyTorch, right? So these are the, two leading deep learning software, right? People use this for academia research and also industry, right? To actually implement, the algorithm on the product. So these are highly mature softwares, right? You basically just have a function call, then you can achieve, gradient descent and to optimize your network, right? And you can just call a function to process the data. So everything is very easy, convenient to use. So you don't have to reinvent the wheel. So it's very easily to prototype and get the idea running. And another reason is we have this GitHub repo, right? So we have this open resource. So people can post their code, source code on GitHub, right? So in this case, you can easily use this kind of existing code, and you can make modifications, and then basically you don't have to implement everything from scratch. This can save a lot of time and kind of avoid a lot of errors, right? Because if you implement an algorithm by yourself, maybe some of the details are not clear, maybe present in the paper or technical report. So you are not able to reproduce the result, then it's going to be hard for you to make any modifications on top of that. But with these kind of open source, for us, it's going to be much easier. So that's why you'll see, basically this area evolve so quickly, right? So you can see every day you have a lot of work posted on arXiv, right? Papers, and you have a lot of people release the code on GitHub, right? So have all those projects there, and you can use. So those are some of the kind of brief background, right? So why deep learning is able to take over in every field, basically, and also gonna be maybe also gonna be the hot trend for the next couple of years, I believe. So let's talk about some of the the basic or fundamentals of machine learning, right? So we can think of machine learning is basically looking for a function, right? So no matter what kind of applications you have, right? For speech recognition, right? So you have a input audio file, right? So you want to output text, right? What is this speech, right? This is maybe a how are you, right? So you have a mapping function, take the input, and you want to generate output, which is the output text. And for image recognition, similarly, right? So you have an image. Maybe I want to do image recognition. That is, I want a mapping function to tell me, right, what is the object category in this image, right? A cat or a dog. And for playing Go game, right? So the input will be this kind of the layout, right? Then you can take image of this layout, right? These two opponents and the current layout of the game, and will take that as input and map to like what is the next move, right? If you are the player, take on the side of white, right? What's the next move? And also for the dialogue system, right? So we can take input, right? Maybe this is the user input, and then we have basically have a mapping function, right? So based on this input, what is the response we should give, right? Based on this user input. So just like a chatbot, right? So I'm sure you've all kind of experienced these chatbots, like the shopping website or maybe banking or any of the customer service. Usually they have this kind of chatbot, right? So you can input some question and they can, based on your input, they can find the corresponding answer or response to you.